Let's see how we can use the chain rule to differentiate the log function. We can rewrite y equals natural log of x as e to the power of y equals x. Then if we differentiate both sides of that equation with respect to x, we will get the derivative of e to the y is equal to dx dx. And dx dx of course is equal to 1, and we can differentiate e to the y using the chain rule. That is, we will differentiate it with respect to y, and then y with respect to x. Now the derivative of e to the y is e to the y, and then we can rearrange that equation and make dy dx the subject, because that's what we're trying to find, the derivative of y, where y is the natural log of x. And we get 1 on e to the y, and e to the y is equal to x. And so we can replace that with an x. So we end up with the derivative of the natural log of x is equal to 1 on x. Now that we know what the derivative of natural log of x is, we'll use it to find the derivative of natural log of 5x. We'll make a substitution, u equals 5x, so that we can write y as natural log of u, which we know how to differentiate with respect to u. So we'll use the chain rule now to differentiate y with respect to x by differentiating it with respect to u, and then u with respect to x. So our derivative of y with respect to u is 1 on u, and the derivative of u with respect to x is 5. And our u, of course, was 5x, so we'll put that back in place of u, and simplifying we'll get 1 on x. So the derivative of natural log of 5x is 1 on x. Now we could have had any number in place of the 5, and we would have got the same result. And so if we replace the 5 with a k, we'll generalize it here, and k is any constant, we would get the result that the derivative of natural log of kx is 1 on x. Now the log function is only defined for a positive input, and so if the k is positive, then log of kx is defined when x is positive. If the k is negative, we would have to make the x negative as well, so that the kx is positive, and then we can take the natural log of it. We saw that the derivative of the natural log of kx for various values of k will end up being 1 on x. So that tells us that the tangents to all those natural log kx functions will have to be parallel. We have two functions here, natural log of x in green and the natural log of 2x in red. And at the point there where x equals 4, we can see that the tangents to those two functions there are parallel. If we take other values of x, you can see that those tangent lines there still remain parallel for all those values of x. We can change our two functions. Here we'll make the second function natural log of 10x, and once again we can see that the tangent lines are parallel. Normally we would view the natural log of kx function as a dilation of the natural log of x function by a factor of 1 on k in the x direction. However, if we use our log laws and express the log of this product as the sum of these two logs, then we can see that we have the natural log of x function that is translated upwards by a natural log of k. So therefore, because it's a translation, we've actually got the same graph just moved upwards. And so for any one value of x, the gradients will be the same for the tangents at that x value. That is, the tangents will be parallel, as we saw. In this example, we'll use the chain rule because we have a function inside the natural log function there. So our substitution will be that inner function uq plus 1, and then we can express y in terms of that u. So the chain rule tells us that to differentiate y with respect to x, we'll differentiate it with respect to u firstly, and then the u with respect to x. So the derivative of y with respect to u is 1 on u, and the derivative of u with respect to x is 3x squared. We'll replace the u once again with the x cubed plus 1, and then that gives us the derivative of y with respect to x, all in terms of our variable x. So in general, the derivative of the natural log of some function u, which will be a function in x, can be obtained by differentiating the natural log function with respect to u firstly, that's 1 on u, and then differentiating the u with respect to x. Now we can rewrite that in the function notation there, where our du dx is the g dashed of x, and the 1 on u is g of x. Our u is just g of x. So in this example, we have a function, natural log, and a function inside as well. So we can simply differentiate that using that result that we just had. That is, we'll differentiate the natural log function to get 1 on our inner function, which is sine x, and then differentiate the sine x. Now, of course, we can obtain that by making that substitution, that u equals sine x, as we did in the previous example. So our derivative of sine is cosine, and so we get the result of cosine on sine, which we can write as 1 on tan x. That is, that the derivative of the natural log of sine x ends up being 1 on tan x. Let's now work out what the natural log of the absolute value of x is. Now, the absolute value of x always returns a positive number. And so we define the absolute value of x as x if x is positive, and it's the negative of x if x is negative, so that it'll turn it into a positive number. So differentiating that, firstly the natural log function of x, its derivative is 1 on x, and the derivative of the natural log of u is 1 on u, where the u is negative x. And then we need to differentiate u with respect to x, so that'll give us a minus 1. And so we'll get 1 on x. So we end up with 1 on x for both of those values of x. And so the derivative of the natural log of the absolute value of x is going to be equal to 1 on x for all values of x, except for x equals 0, where the natural log function is undefined. So we've seen that the derivative of the log function is simply 1 on x for all values of k except for 0, and that the derivative of the natural log of the absolute value of x is equal to 1 on x.